Hello guys, welcome back to the channel, but before we start, make sure to smash that like and subscribe button. The relatively calm region of space we occupy in the solar system today belies a fiery, violent past, and a spine-chilling future. This video explores the geological and natural history of Earth, beginning with the formation of our solar system, moving on through asteroid impacts and mass extinctions, and ending with the human impact on the environment today. To really grasp the magnitude of the changes our planet has undergone, we need to speed through immense time scales, pausing at important milestones. And this video, the first of the series, starts at the very beginning. Some 4.6 billion years ago, a giant cloud of gas, called a nebula, collapsed into itself because of its mass and crushed all the gassy material in it into a plane, even as it was constantly spinning. This disk of material is called the protoplanetary disk. Over a period of 100,000 years after the collapse, the Sun was formed at the center of this disk, with the rest of the nebular gas swirling around it. Nearly 98% of this gas was just hydrogen and helium. Our Sun constitutes 98% of the mass of our solar system today. Gases and other materials in this protoplanetary disk outside of the Sun started clumping together at various spots. Constant collisions between these bodies formed miniature planets, called planetesimals. These seeds of planets eventually grew in size by pulling more material in due to growing gravitational forces, a process called accretion, to become true planets within 100,000 years after the Sun's formation. The gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune, formed much faster than the four terrestrial planets, Mercury, Venus, Earth, and Mars, did. Approximately 4.54 billion years ago, a Mars-sized body slammed into the newly formed Earth, partially liquefying the surface and ejecting molten debris into space. This ejector remained as a ring around our planet for a few months, before coalescing and forming the Moon. Residual gases were still swirling slowly around the Sun, causing streams and waves in space. Elephantine Jupiter got caught up in these currents and started moving inward toward the Sun. The movement of this giant, with its powerful gravity wreaking havoc as it danced around, dislodged asteroids and sent them flying inwards into the planets. In the next few million years, the Earth and other terrestrial planets went through a period of constant battering by asteroids and other smaller bodies. This period in the solar system's history is called the Late Heavy Bombardment. Fortunately, Saturn soon started pulling Jupiter back toward where it is today, even as the solar wind stripped away all of the residual gas in the solar system into interstellar space. At this point, Earth was still cooling from the formation of the Moon, and the period of bombardment kept it agitated and volcanically active. At some point, asteroids or comets containing water ice slammed into the Earth, thereby bringing a lot of water vapor to the Earth. Once the Earth cooled, this vapor condensed and fell as rain on the planet. Volcanic activity still continued, and even under the newly forming oceans, supervolcanoes persisted. Lava constantly flowed on the surface for nearly 700 million years. We know all of these intricate details to a near approximate date by studying rocks on our planet. Rocks hold records of all kinds of transitions that they have undergone. They record their own formation and grow over millions of years, keeping evidence of life and planet activity within. The field of geology that studies and dates rock layers is called stratigraphy. This helps scientists figure out the age of a lot of geological processes, and has enabled them to put together a geological time scale for our Earth. The geological time scale above is a representation of time elapsed after the formation of Earth, divided into slices, each differentiated by a geological event whose record is held in rock samples. Geological time is primarily divided into eons, which are divided into eras, which are further divided into periods. A discussion of these three scales falls within the scope of this series. However, for the sake of completeness, it needs to be specified that periods are further divided into epochs, and epochs into ages, while eons are grouped into supereons. The first three eons are grouped under the Precambrian supereon. The fourth eon, called the Phanerozoic, is ongoing. Although the first three eons together account for most of Earth's history, stretching out for nearly 4 billion years, there was little of note in terms of biological activity or geological diversity. So, in representations such as the table above, they are usually collectively called the Precambrian. It contains the Hadean Eon, when Earth was forming and the late heavy bombardment took place, the Archean Eon, when water first showed up and the first life forms evolved, the Proterozoic Eon, when the first multicellular organisms appeared and Earth's atmosphere received oxygen for the first time as a result of the proliferation of cyanobacteria. The early years of the Precambrian saw the formation of the Moon, a molten Earth slowly cooling down, and the planet getting battered by small runaway bodies. Water vapor in the atmosphere from asteroid and comet impacts started to condense and rain down on the planet as liquid water. Oceans formed amid heavy volcanic activity. Portions of the surface periodically cooled off to form occasional land masses, but they would immediately be swallowed up by lava. Then, approximately 100 million years after the Earth formed, the temperatures had become stable enough for a crust to form and survive. The atmosphere was heavy and toxic, with almost no oxygen but with large amounts of carbon dioxide, nitrogen, and sulfur due to volcanic activity. Within another 500,000 years, multiple tiny land masses had been born. These went on to become the center around which present-day continents formed. The oldest known rocks on Earth are from this period, now in Australia, dating back to 4.4 billion years ago. Sandstone rocks in Jack Hills in Western Australia, in which 4.4 billion-year-old zircon crystals were found. Source: author provided. Towards the middle of the Precambrian, the Earth had cooled sufficiently. In the atmosphere, there was still no oxygen. The oxygen on our planet today is produced and sustained solely by plant life. This lack of oxygen implied a lack of ozone to protect the Earth, which exposed the Earth to UV rays from the Sun. However, the Earth's atmosphere could be preserved because its magnetic field had begun to form. This protected the atmosphere from being stripped away by the solar wind, as the atmosphere of Mars was. Around 3.5 billion years ago, two supercontinents, called Valbara and Ur, formed within 500 million years of each other. These land masses were actually quite small, probably about the size of India. But since they were the only land masses around, they are called supercontinents. The lack of oxygen in the atmosphere did not mean a lack of life, though. Life began on Earth in the early Precambrian, 4.1 BA, when Earth had just started cooling. Gems from this time period, called zircons, have very specific carbon ratios, and possibly show evidence of biological activity combined with water. It is commonly assumed and accepted that one of the main causes of the creation of life is the presence of large oceans. Liquid water is considered to be a universal solvent, which means that it can transport all kinds of nutrients to all corners of the planet, enabling even the remotest locations to support life. Thanks to its almost magical properties, the very presence of liquid water on a body is a giant attraction for space exploration today. Apart from nitrogen, methane, and ammonia, volcanoes also released a lot of carbon into the atmosphere. Coupled with the condensing water vapor, Earth became a crucible for the formation of life in this early environment known as primordial soup. Simple cells are believed formed in such a wet environment. Small ponds that could have been struck by lightning or another form of energy, and deep-sea hydrothermal vents that contain the energy and nutrients to synthesize a cellular structure could have been likely location for the formation of life. Scientists have not been able to artificially recreate the synthesis of life. How life came to be remains an enduring mystery. Nevertheless, water was the only medium to contain the earliest life forms, which were unicellular. These could simply absorb nutrients from their surroundings and break it down in their system for sustenance. This very primitive process made life dependent on nutrients from rocks and water. But towards the second half of the Precambrian, early unicellular bacteria started absorbing infrared light instead of visible light and started to emit oxygen. This was primitive photosynthesis. Photosynthesis enabled organisms to create their own food for the first time. This mechanism offered a great advantage and accelerated the growth of life, from prokaryotes to eukaryotes that started reproducing sexually 1.2 bia, to multicellular life. Banded iron formations, layers of rock from the ocean showing pulses of iron oxide deposits due to reaction with oxygen, dating back to 3.7 bia exist today. These show evidence that large quantities of oxygen were pumped into water at intervals, a phenomenon that is explicable only as a biological process. More biochemical rocks, called stromatolites, that were formed due to microorganisms trapping sand grains to build colonies, date to 3.5 bia. The most solid evidence of photosynthesis, however, dates back to 2.4 bia when cyanobacteria flourished, infusing massive quantities of oxygen into the air. So, 2 billion years after the Earth formed, there was finally a constant supply of oxygen in the air for the first time. At around the same time, a new supercontinent called Kennerland was formed, while Valbara broke up, with parts of it ending up in today's Australia and Africa. Kennerland was much larger than either Valbara or Ur. It was as big as Africa and existed somewhere near the equator for 100 million years before breaking up. Meanwhile, the Earth's atmosphere underwent a drastic change as photosynthesis increased. It evolved from a nauseating mixture of carbon monoxide, methane, ammonia, and nitrogen, to becoming much more toxic with plenty of pure oxygen that was anathema to the existing life forms. Pure oxygen today still remains toxic to all life, including humans. Since cyanobacteria were aquatic, they saturated the oceans with oxygen too. This was called the Great Oxygenation Event and occurred 2.3 bia. The rise in levels of this new gas in Earth's ecosystem led to two major events on Earth, the first extinction event and the first ice age. An extinction event, more commonly known as a mass extinction, is the extinction of a large number of species within a short period of geological time. There have been 24 extinction events in all of Earth's history, before humans came around 200,000 years ago. 5 of these were particularly destructive, with detailed, well-documented evidence of their occurrence and repercussions. These major extinction events are called the Big Five. Mass extinctions always occur after a sudden, rapid, and uncontrollable change in global climate, which is obvious because only such widespread changes can kill off diverse species spread out over land and water in a short period of time. Conversely, mass extinctions could also affect the global climate, as disappearance of a majority of life on Earth could upset the oxygen balance. As photosynthesis increased, there were very few life forms that were able to consume enough of this new oxygen. There was nowhere for the toxic oxygen to go because there was no oxygen sink. As the oxygen content in the atmosphere and oceans increased, early life that was just forming was also dying away rapidly. This is why the Great Oxygenation Event also became the first known extinction event. The other effect the oxygen catastrophe had was the formation of glaciers. The rise of oxygen naturally removed a lot of greenhouse gases from the atmosphere, most notably methane. Oxygen lowers temperatures, which is why wooded areas are so much cooler than cities today. The saturation of oxygen in the atmosphere lowered the overall temperature to 5 degrees Celsius lower than today and removed the ability of the atmosphere to keep the planet warm. Temperatures started falling steeply, heralding an ice age. An ice age is a period, extending to millions of years, of lowered temperature on the Earth. A characteristic feature of an ice age is the presence of continental glaciers and polar ice caps. An ice age is composed of periods of extreme cold, called glaciation periods, marked by the appearance of large ice sheets and glaciers over continents. These alternate within the same ice age with periods of warmth, called interglaciation periods, where the ice sheets are confined to the poles. The ice age caused due to the Great Oxygenation Event was the first of the 5 ice ages the Earth has seen and is called the Huronian Ice Age. We are currently in the middle of the 5th Ice Age's interglaciation period. The next installment in the series discusses the Huronian Ice Age, the Cryogenian, or the Second Ice Age, the breakup of the Kennerland supercontinent and the formation of new supercontinents, as well as the first of the 5 major mass extinctions, and gamma ray bursts.
morninglightmusic.io